In chapter 5, Albert is going to ask the question of when, if, when and under what circumstances the second law of thermodynamics can be broken. And thought experiments where the second law of thermodynamics might be broken are usually labeled thought experiments about Maxwell's demon. So the original demon envisaged by Maxwell is standing between two containers of gas, one of which is hot and one of which is cold. Right? And what Maxwell himself had sort of shown and calculated is that in a hot container of gas, the average speed of the molecules is higher than the average speed in the cold container of gas, but not all molecules have the same speed. In fact, there are slower and faster molecules, and this means that some of the molecules in the hot container of gas will be slower than most of the molecules in the cold container of gas, and some of the molecules in the cold container of gas will be faster than most of the molecules in the hot container of gas. And so you can then have this thought experiment where there is a little demon standing beneath these two gases, and he has a little door that he can open. And whenever a very cold molecule from the hot gas, a very slow molecule, I should say, from the hot gas approaches the door, he's going to open the door so that the slow molecule can go to the cooler gas and make it even cooler, while the hot gas, which loses a slow molecule, gets a little bit hotter. And whenever an especially fast molecule from the cold gas approaches the door, he's also going to open it so that this especially fast molecule can go through, heating up the hot gas and meanwhile cooling the cold gas. And so Maxwell's demon would be able to make the hot gas hotter and the cold gas colder, which is a violation of the second law of thermodynamics. And so we could wonder, well, is this scenario possible? And if we say yes, why don't we see it around us all the time? But if we say no, why is it impossible? I mean, the way I described it, it certainly seems possible. So why would this be impossible? Now, one way to try to do this is to try to come up with certain mechanical devices that could function as a sort of Maxwell's demon. And maybe one of the most simple devices would be one that doesn't really react to a hot and a cold gas, but that reacts to a gas at high pressure and one at low pressure. So if I can increase the pressure of the high pressure gas while lowering the pressure of the cold of the low pressure gas, that would also be a violation of the second law of thermodynamics. And we might think that this is actually very, very simple. Right? All that we need is a one-way door, right? A kind of valve, like there's a little hole in the wall between these containers, and there's a little door with a, that can swing, such that if a molecule from the low-pressure gas hits it, it's gonna push it open and go through. Whereas if a molecule from the high-pressure gas hits it, well, it's just gonna get more closed. It gets slammed into the wall. It doesn't open. And then molecules from the low pressure gas could go to the high pressure gas, but molecules from the high pressure gas couldn't go to the low pressure gas, and we have a Maxwell's demon. So why doesn't that work? Right? Why don't we make it? Because if we could make it, then we could use those pressure differences to actually generate, useful energy. We could use that. It's basically how a wind turbine works, right? Or a windmill. You use pressure differences in the air in order to generate energy. So why doesn't it work? And one story that you can tell about this is that there's a little door. I mean, it has to be so light, right? It has to be so light and so easy to open that these single slow molecules can push it open and go through to the other side. But that means that the energy needed to open this door is so small that even the random thermal fluctuations of the sort of molecules that make up this little door itself and make up the walls to which it is attached, those energy fluctuations will be enough to open it. So actually this door has to be so easily opened that merely through the fact that it has the same temperature as these gases, it is going to open itself all the time and it's not going to work. That's sort of the standard story that you can tell here. And so, well, so what? Right? We can't conclude from that Maxwell's demon is impossible, that there can't be any such thing as Maxwell's demon. All we have shown is that one particular mechanism doesn't seem to work as a Maxwell's demon. So, can we give maybe some general theoretical argument? Well, here's one way we might want to think about that. Right? We might want to say, oh well, surely Maxwell's demons are possible because having done statistical mechanics, we know that the second law holds only probabilistically. And so we could take two containers of gas and put a hole between them, and there will be circumstances where just by luck, the fast molecules will move through the hole to the hotter gas and slow molecules will move through the hole to the colder gas, and then we would have a violation of the second law of thermodynamics. And so Maxwell's demon is sort of trivial. It's just that, its probability of working is extremely small. So that's one way to think about it. But then, that's not really what people mean with Maxwell's demon. Right? Maxwell's demon, we could say, is supposed to work reliably. If I have a hot and a cold gas, then Maxwell's demon should be able to make the hot gas hotter and the cold gas colder, no matter the actual circumstances of those two gases at this moment. Right? No matter how they are sort of behaving right now, no matter where their molecules are exactly, Maxwell's demon should be able to make this work. And just having a random hole, that's going to work for very particular initial circumstances of these gases, but it's going to fail for most of them. So in order to be a real Maxwell's demon, we want something that works irrespective of the precise initial conditions of the system that it's going to work on. Okay, so let's think again. Do we have any general arguments in favor of or against the possibility of such Maxwell's demons? Well, here's one way to think about it. You could say, look, what we have learned from thinking again about statistical mechanics is we have to think of the phase space of the gas, right? All the possible situations that it could be in. And we have learned about Liouville's theorem, which says that if we start out with a bunch of possible initial states, like there's a part of phase space where the gas could be at the beginning of our exercise, then as the system evolves, the amount of phase space that gets covered by all of the places where we've evolved to has to remain the same. Right? You can't get any smaller in phase space. And so suppose that we start out in a very large macrostate in such a way that the macrostate is entirely filled up. Right? All we know about the gas is that here the temperature is 20 degrees Celsius and here the temperature is 0 degrees Celsius. And we know their volume and how many particles there are. That's what we know. We don't have any details. So we only know the macrostate. And every, position in the macrostate, every way that the gas could be that fits that macrostate is equally probable, equally possible. It's something that Maxwell's demon would have to be able to work on. And so we start out with this big macrostate entirely filled. And now if Maxwell's demon tries to lower the entropy of the gas, right? And lower entropy means a macrostate that is smaller in phase space. It's got to get all this volume into this much, much, much smaller volume, which is by definition impossible. Well, not by definition, but by Liouville's theorem and sort of ideas that we have about mechanics. It's impossible. You can't fit the large thing into the small thing because it has to remain equally large. And that is sort of true, but only if we fail to realize that that volume could be generated, so to speak, somewhere else. Namely, maybe in Maxwell's demon itself, or in some other system that Maxwell's demon has access to. So if we have a large macrostate of potential initial states of the gas, well, we could get it into a macrostate that is 2 times as small, provided that Maxwell's demon himself goes from one initial state to 2 possible initial states. That is actually perfectly all right, because then, while one volume is twice as small, the other volume is twice as large, and it's going to cancel each other out. So, although the volume has to be preserved, the volume in phase space, it doesn't have to be preserved in the original system that Maxwell's demon is working on. It could, for instance, be preserved if we look at the combination of the system and Maxwell's demon, or the combination of the system and some other system that Maxwell's demon can work on. Now, all right, one thing that we could think is that this means that once again, the second law can't be broken. Because suppose that Maxwell's demon takes this gas and reduces its phase space, right? It makes it one of the ways you could sort of put something in a smaller phase space is to, in a smaller macrostate is to cool it down. But then the energy has to go somewhere else, and Maxwell's demon maybe has to heat up himself, or he has to heat up some other system that he has, and then there the volume in phase space is going to increase. And that might not be, if the volumes decrease and increase in the right ratio, that might not be a violation of the second law of thermodynamics at all. Right? It could be the case that the entropy gained by Maxwell's demon is just as much as the entropy that the system loses, and then the total entropy would remain the same, which is fine for the second law of thermodynamics. So we might think that as soon as we start thinking about Liouville's theorem and volumes in phase space, we can see that entropy actually can't go down at all. Right? Entropy can't go down because whatever this system, like the gases for instance, loses in entropy, well, some other system, the demon or a third system that the demon has access to, is gonna get, right? That entropy is gonna increase by just as much as this entropy is gonna lower. And if that were the case, right, if that's the conclusion that we have to draw, it would maybe actually be fairly problematic. Because if we can use Liouville's theorem to show that the entropy, the total entropy of all these systems together can't go down, then it seems that we should just as well be able to use it to prove that the total entropy can't go up. But of course, entropy does go up sometimes, and there must be something wrong with the way that we just reasoned. Well, actually, there might be several things wrong with the way we just reasoned. And one of the things that Albert does is he does a pretty good job in distinguishing several of these scenarios. So one scenario, one that he ends up calling Pseudo Maxwellian demons, I don't think I've seen it anywhere else, and I think it's very interesting. It's this. Suppose that you have a Maxwell's demon which takes a gas, right, which can be in any initial system, and then it rearranges the molecules in such a way that this gas is gonna, let's say, coalesce in one corner of the container, and so drastically lower its entropy. Not now, but 1 hour from now, right? So he's calculated all these trajectories of all these particles, and he thinks, well, if I change this and this and this and this, and he makes a bunch of changes, maybe many changes, and then the system remains isolated. Maxwell's demon goes away, goes on holiday, and after 1 hour, suddenly all the molecules start moving towards one corner of the container, and the entropy gets drastically lowered. And maybe while he was doing this, Maxwell's demon had to increase his own entropy dramatically, or maybe he had to increase the entropy of some other system dramatically. Well, in a sense, we're still breaking the second law, right? Because here is this isolated system. Maxwell's demon has gone on holiday, and suddenly it lowers its entropy. Right? And it reliably lowers its entropy, and we can know in advance with perfect certainty, if we know that Maxwell's demon works, we can know in advance with perfect certainty that it is going to lower its entropy. So there we have a breaking of the second law of thermodynamics through a kind of delayed action. Right? Yes, there was an entropy increase here, but now we've got this isolated system which is actually breaking the second law of thermodynamics. It's just that we paid for it with an entropy increase at some earlier time. So I think that's a really interesting scenario. It's maybe not quite what people meant when they were talking about Maxwell's demon, which is why Albert calls it Pseudo Maxwellian demons, but there is nothing in thermodynamics or in statistical mechanics that forbids this idea that you could have a system which is right now isolated, and you can know with perfect certainty that it's going to lower its entropy. Right? There's nothing that forbids that, and the pseudo-Maxwellian demons show it. Okay, but what about real Maxwellian demons? Right? Could we have something, a demon, that is able to take a gas or two gases or whatever in whatever microstate it is, and actually really lower the entropy without the entropy anywhere else going up? And again, I said that the best theoretical reason for believing that that's impossible is because this higher entropy is a very big macrostate, and the lower entropy of the gas is going to be a smaller macrostate, and so that volume needs to go somewhere. And now we might think that if we look not just at the gas, but at the gas plus Maxwell's demon, plus any external things that he might be using, so we have a bigger system. Well, it starts out in a large macrostate, and if Maxwell's demon is supposed to lower the entropy of all of this stuff together, of the gas and himself and any external systems, then he has to take all the phase space in this big macrostate and put it into a small macrostate, and that's impossible. But actually, that is not impossible. And here we see that there's an assumption that we have made in basically every discussion that we had until now, where we talked about phase space and volumes in phase space. And it's an assumption that is maybe true for certain systems, like something as simple as a gas in a container, but that we have no reason to believe is true in general. And that is the assumption that the volume of the biggest phase space, that the volume of the biggest macrostate in phase space is going to be much larger than the volume of all the other macrostates in phase space combined. Because it's one thing to be the biggest thing, like the biggest macrostate in phase space, and of course it is something totally different to be the majority of phase space. Here's an example. I mean, suppose that you take a random walk through Manhattan. And it's random, so let's say that you are just as likely to be at any point of any street at any time as any other point of any other street. Well, let's take all the streets as our macrostates, right? The only thing that we're going to know about you is in what street you are. Like, that's your macrostate. Then the macrostate that you are most likely to be in is going to be the one with the biggest volume in phase space, which is the longest street, which I think is Broadway. Right? So Broadway, Manhattan, has the largest macrostate, it has the largest volume in phase space. But that doesn't mean that you are very likely to be in Broadway when you are walking randomly through New York. In fact, you're very unlikely to be in Broadway because there are so many streets, right? And although Broadway is the longest, it's not that much longer than all the others that it sort of fills half or more than half of phase space. It still fills only a fairly small part of phase space. So, suppose that there is some high entropy state, so it's very large in phase space. But suppose that there are just many more lower entropy states, but there are so many of them that because they are with so many, even though they're smaller, together they're bigger, right? Together they're bigger than this big macrostate. Then a randomly evolving system is going to spend most of its time in one of these lower entropy states. And you might be able to think up systems, especially because we are kind of the people who decide what counts as a macrostate, right? I mean, that's not really in nature itself. It's like how we measure, how we think of things sort of determines what counts as a macrostate. And there's absolutely no rule forbidding that the vast majority of phase space is filled with very small macrostates, whereas the big macrostates fill only a small part of phase space. Right? All you need for that is that there are many of these small macrostates and only a few of these big macrostates. And so there doesn't seem to be either anything wrong with a system that simply, like randomly walking, spends most of its time in low entropy states. But there also doesn't seem to be anything wrong with a Maxwell's demon, who takes a system that is right now in a large part of, like in a large macrostate, and then it puts it into not one small macrostate, but into one of many small macrostates, right? Depending on the initial position of the system, we might get into one of many small macrostates. So, for instance, suppose that there's a demon who is going to use the energy of a gas. So it just has a gas at a certain temperature, and it wants to use this energy, this heat, in order to raise a weight. Right? That is usually forbidden by thermodynamics. Right? You can't take this hot gas and do nothing but cool it down and raise a weight. I mean, that would be a way to turn heat into useful work without having anything else needed. That would be a very clear violation of the second law of thermodynamics. Well, certainly our argument about phase space can't show that this is impossible. Like, what it can show is that it's impossible to have a system where you have just this one hot container and one weight, and you use the heat to raise this one weight and do nothing else in the world, because then the volume in phase space of the gas is going to decrease by a lot, whereas the volume in phase space of the weight, it's going to stay exactly the same, right? It used to be in one possible position, it ends up in, let's say, still one possible position. But that's because it's one weight, right? What if we use 1 trillion weights? Well, then it seems that suppose that we raise one of 1 trillion weights, depending on the initial state of the system. Then it seems that we should be able to make the volume in phase space of the original gas 1 trillion times smaller, because there's also now 1 trillion times more options in the phase space of these weights. Everything comes out all right in our calculations. Right? Liouville's theorem does not forbid this. And we might be able to think of more efficient ways to do this than to use 1 trillion weights. I mean, we could just use, let's say, a lot of weights, but raise some of them to different degrees, and then we could have generate a lot of different macrostates, which are all a lot smaller than the original one. And that way, we might conceivably use the energy of the gas in order to create useful work or something like that. We might go from a high entropy state to a lower entropy state, breaking the second law of thermodynamics reliably without ever getting into trouble with Liouville's theorem. And so, as far as we can see, as far as Albert can see, and as far as I can see, there is here no fundamental reason why there couldn't be Maxwell's demons. And that is pretty surprising, given that usually we are told that there can't be Maxwell's demons. Well, maybe there can be Maxwell's demons. Of course, this generates some questions, right? Some questions about, well, why don't we actually do this, right? Is it too hard to build such a system? Is there a way to sort of get a better second law that explains why making such systems is not going to work? Or that is gonna use ideas of, let's say, a cycle or, whatever, some new theoretical terms in order to explain more exactly what we would actually be able to do or see in practice and what not. And to a large extent, we don't know. I mean, there's lots of people who have tried lots of things, but I don't think, and Albert here doesn't think, that there's some kind of general answer to that. That we, at the moment, have a very good theory about, well, why exactly or when exactly Maxwell's demons would it be possible. I like to point out, and now I step away from the book and talk about the master thesis I wrote back in 2004, I think it was. Yeah, I think it was 2004. In my master thesis, which was about Maxwell's demon, I suggest that, the fact that we can't turn heat into useful work in practice seems to have a lot to do with the fact that the particles that we want to extract heat from are basically the smallest ones that we could sort of manipulate or make useful things out of. Like, if you can, for instance, build this tiny trapdoor out of particles that are orders of magnitude smaller than molecules, well, then all the multiplicity, like all the volume in phase space, could get into the movements of those super tiny particles, which wouldn't have a temperature in the same sense as the molecules of the gas would have. And then I don't think there's a theoretical reason why you couldn't do that. So it is sort of theoretically possible if you had a room with a lot of fast-moving, very elastic balls that are bumping into the walls, etc. I mean, then you can build a trapdoor that they can bump into, and the balls end up in one end of the room. And you can do that because you don't have to build the trapdoor out of things that follow the same laws as those balls, right? They're much smaller and so forth and so on. If you could do that for molecules, so using something that's a lot smaller than molecules, maybe you could get energy from the molecules as well. And all the volume in phase space could sort of bleed from the level of molecules to the level of these extremely tiny particles where you would never see it or miss it or whatever. That's going to be a lot harder to do in practice if we want this multiplicity of the phase space of the gas to go into different macrostates. Because the multiplicity of the phase space of the gas, like the volume of the phase space of the gas, is really big because there are so many particles in a gas. And if you think about the number of macroscopic objects that you would have to use in order to build a Maxwell's demon that doesn't break Liouville's theorem and is able to get a serious amount of energy from a gas, it is going to be gigantic, right? I said 1 trillion weights, and even 1 trillion weights might not be enough to get a serious amount of energy from the gas. You might have to be many, many orders of magnitude higher than that, and that doesn't seem to be very practical. I mean, how are you going to build that in such a way that you can manipulate all of that without losing the energy? There's nothing sort of theoretically forbidding it, but it doesn't seem very practical. Okay, that was a sideway. I mean, that's not a side discussion. That's not in the book. The conclusion that Albert has at the end of this chapter is that Maxwell's demon seems perfectly theoretically possible, but maybe, and we haven't done it yet, but maybe we need to think more deeply about sort of ways in which we could formulate a version of the second law that can't be broken. All right, the next chapter is going to take a look at how thermodynamics and statistical mechanics, and especially something like the need of the past hypothesis, interacts with philosophical ideas like knowledge and intervention and action. So stay tuned for that. Thank you.